But there's one thing that's left, and that is the Jacobian. So you need the Jacobian of x, y, and z with respect to u, v, and w. Now, since that completes the change of variables, and normally that would be a real pain, because what you'd have to do is compute the determinant of xu, xv, xw, yu, yv, yw, zu, zv, zw, and do a 3x3 determinant. However, that's not going to be bad in this case, because in this example, most of them are 0. So you just have dx du, which would be 2u, y dv would be 2v, zw would be 2w. So what you end up getting, you just multiply all these together. So this turns out to be equal to 8 UVW. And that's what you'll integrate. But you can kind of see that, well, by the time we start working out these integrals from the innermost out, it might get a little nasty. You saw in number 6 in the second exam, I put an integrand of x, y, z, and you saw what happened with that. Don't worry, I will work these out completely and screen them to make sure that the integral, you don't get something that's going to go on for a page or more. Yeah.
So the final exam isn't final yet?
I'm going to do a once over to make sure
Okay.
that it's good, but yeah, I feel pretty good about it. So the all right. Certainly the setup for these is very important. If the setup is good, I'm less concerned about the result of the actual integration. Okay, so if you're given a change of variables, so here the integrand is just 1. If the integrand was something else, you'd have to substitute these into it. Compute a Jacobian, compute your limit in terms of the new variables, because that should be a nicer region. Maybe it's something like a rectangle or a box where the limits are constant. Because that's the whole idea behind doing a change of variables, is that the region you're integrating over, the integral should be easier to set up. I mean, I wouldn't want to try to set up this, and actually I did try. No, you don't want to do that. So questions about this kind of problem?